Okay, now that we've learned a method for synthesizing primary amines, we need to think about how would we make tertiary amines or secondary amines selectively, and how can we control the different groups that are present around the nitrogen. So to do this, we're going to use a method called reductive amination. So this combines some of the reactions we learned earlier in um, topic 4, I believe, where we learned about making imines and enamines. And so this will involve the reaction of a ketone and either a secondary amine or a primary amine. So if we combine a secondary amine and a ketone, we know there's going to be a number of addition reactions, loss of water, and eventually we'll form this iminium. Note that there's a number of other species around, but this is going to be the key electrophilic intermediate that will be useful for the reaction. In order to convert an iminium to an amine, we need to affect a reduction, right? So we need to have some sort of hydride be able to go in and attack this iminium. So this actually should be fairly difficult because usually whenever we have things floating around, normally whenever we are forming iminiums, we have water present and usually a little bit of acid catalyst. This is challenging because things like lithium aluminum hydride or even sodium borohydride will rapidly do acid-base chemistry with water or protons to make hydrogen gas. So in order to do this reduction, we're going to introduce a new reagent, and this is sodium cyano borohydride. So if we look at the structure of the cyanoborohydride, this is an even milder reducing agent. It does not reduce aldehydes or ketones. You can see that on the grid. It's still negatively charged, so it's a nucleophilic reagent, but it's a very mild hydride source. So it can't donate these hydrides, but it needs to have a very good electrophile. And the very good electrophile will be something like an iminium that is positively charged. And since this is now an activated electrophile, we can have sodium cyanoborohydride add one of its hydride sources into the iminium to make a neutral tertiary amine. So depending on the R groups on this secondary amine and the different groups on either side of this ketone, and this could also be an aldehyde, we're able to now make different types of amine derivatives. So if looking at another example, if we were to combine a primary amine and an aldehyde, this can give us in equilibrium a new intermediate species. Usually there'll be an acid source, so a lot of times there's a little bit of acetic acid around. Again, acetic acid does not directly react with sodium cyanoborohydride because this nitrile group is an electron withdrawing group that takes electron density away from the boronate center. In this equilibrium, we're going to have some protonated iminium intermediates, where this R group is still on this nitrogen. And this will give us secondary amines as the product. So depending on how much aldehyde you have, you could potentially have this go twice or just stop here. You can preform the imine and controllably introduce either one. If you ended up wanting to install two of the same groups onto this primary amine, we could have more benzaldehyde and sodium cyanoborohydride added to now give you two groups. Or we could bring in a completely different type of aldehyde. So we could call this R2 aldehyde in a separate step. And we'd be able to control all three substituents on this amine. So reductive amination offers a pretty powerful way to make amine derivatives, especially since you can do these iteratively, one step at a time to introduce one functional group, then introduce a secondary substituent. And it's, of course, important to recognize that cyanoborohydrides are only reactive with iminiums. It is the positive charge that lets them be reactive, whereas ketones and aldehydes are unreactive under the same reaction conditions. I would refer to the synthesis sheet. I've detailed some of the retrosynthetic logic of how you could build up molecules this way. And usually it involves going retrosynthetically to go and cut different bonds either here, here, or here to go back to their corresponding carbonyl counterparts. This last set of reactions largely is also just a review of things we've learned before. There are some little differences that I'd want to point out along the way. So we know that if we have something like an alkyl bromide, we can actually also make primary amines, but going through a nitrile intermediate. So in this case, we would have something like, go back to my purple color. To introduce this, we would just need sodium cyanoborohydride and DMSO, not DCM. This would introduce a nitrile. Note that a carbon atom is added. So when you go through this process, this will let you at the same time add another carbon unit to the alkyl bromide you started with. So this would be different than using sodium azide in reduction or something like the Gabriel synthesis along the way. Now going from a nitrile to an amine, we just learned how to do this past section. This is lithium aluminum hydride followed by some sort of aqueous workup. There are some other ways to do reductive amination to make primary amines. So if you try to just use it with ammonia, sometimes you do get over reductive amination where it reacts too many times. But we can add in things like hydroxylamine to first make an oxime. This will be a stable intermediate that can be isolated. And this can be reduced using slightly different conditions. These will use single electron reducing conditions. So this is sodium, metal, and ethanol. This will cleave the NO bond and do further reductions. You don't need to worry about this mechanism, but this is an effective way to make primary amines starting from a ketone without having to use ammonia, which can have problems. And the last approach is that we can also make different types of tertiary amine derivatives using reductions of amides. So if you had an acid chloride, you can displace with your amide of choice. This could be ammonia or a primary amine or a secondary amine. And then using lithium aluminum hydride, usually heat is involved, followed by an aqueous workup will give you a tertiary amine as a product.